Hello everyone, I'm Hossein Dadashi, Fashion Engineer at Wise Grid Energy. In this webinar, we are going to talk about ton delta measurement. These are products of Wise Grid Energy, Alternative One, which is a multifunction substation test system. You can test all substation equipment like our transformers, CTs, CVTs, circuit breakers, grounding greens, and so on by this device. A Captain 12 is the 12 kV ton delta and capacitance test system, and MCM1, which is a motor condition monitoring device based on current signature and vibration signature analysis. For more information, you can visit our website, wisegridenergy.com, or you can directly send us email to info@wisegridenergy.com. We will review and we will contact you as soon as possible. So, about ton delta measurement. For an ideal insulation, we can model the insulation by the capacitor, which is called CP here. If we apply sinusoidal voltage to this capacitor, the current passing through the capacitor, I mean ICP, will be 90 degree the phase between the current and voltage will be 90 degree. I mean exactly 90 degree. So in this vector diagram, you see that ICP is leading 90 degree from applied voltage. This insulation can be an XLP insulation, I mean the XLP cables. So between HV conductor and metallic sheets, we have this insulation and we can model it by the capacitor CP. But in a real world and real insulation, we have a loss and we call it uh, ton delta or dissipation factor. What does it mean? We can model a loss of the insulation by RP in parallel with CP. So current passing through RP and CP is the vector sum, and we have I. So if we look at the vector diagram, we see that the current passing through the source, I mean I, doesn't have a 90-degree phase shift according to the applied voltage. And it deviates by delta from 90 degree. So we call this delta loss angle, and tan delta is called the ratio of the IR to IC, or the ratio of P to Q, which shows us the power losses of the insulation. And here we found that okay, we have a real insulation and there are losses in this insulation, and we can model this loss by RP in parallel to CP. Uh, and this loss is called tan delta, which is the ratio of the resistive current to the capacitive current. And the higher the resistive current, the greater the insulation losses, and which leads to heating and potentially serious insulation problems. So there is another point, another related concept, which is called power factor, as shown in this diagram. In addition to tan delta or the delta angle, we have another angle which is called phi, and it is the complement of the delta angle. I mean 90 degree minus delta is equal to the phi. And cosine of this angle is what we refer to power factor. In many American standards and practices, power factor is used instead of tan delta, and we can convert the power factor to dF by these equations. But in tan delta values up to 10%, it's not necessary to convert these values together, and you can use PF instead of DS or vice versa. An important question here is what factors affect tan delta? So first, tan delta is a material property, and it depends on the type of the insulation material. For example, solid insulations generally have higher tan delta values than liquid insulations, and liquid insulations have a higher tan delta value than gases. So tan delta is intrinsic characteristic of the insulation material. Uh, Second, we model the insulation using a parallel resistor with a capacitor. But where does this uh, loss actually come from? Let me to talk about it more. So there are two main sources for this loss. First one is the conduction loss, which is related to the insulation resistance, what we measure at the insulation resistance or Maillard test. The second one is the polarization loss, which happen inside the dielectric due to the molecular behavior. We will discuss this in more details later. These two mechanisms together determine the dielectric total loss, and the third and very important one is the time delta dependency on temperature, humidity, and frequency of the applied test voltage. Because of conduction and polarizations, which are both nonlinear phenomena, this dependency is complex and doesn't follow a simple mathematical relationship, and we will explore more in the upcoming slides. So, about the polarization mechanisms. Different polarization mechanisms occur inside the insulating materials. When an electric field is applied across an insulation, molecules inside the material uh, align along the field direction, and this phenomena is called polarization. Polarization can happen at various and different levels. At atomic levels, positive and negative charge can slightly shift uh, along the field direction, even affecting electron clouds. Second one is the materials structure-based polarization, which dipolar groups can reorient themselves along the fields, and it's called lattice polarization. Some materials may contain dipolar molecules or permanent dipolar molecules, such as water molecules, which strongly aligns when the field is applied. And for example, in a transformer insulation, moisture presence means that water molecules inside the materials also align with the field. Another type is the interfacial polarization, and which means that the polarization occurs at boundaries between two different insulating materials with distinct structure and properties. These different type of polarization can occur at different frequencies and temperature. So because of this, when measuring tone delta and capacitance of a material over varying temperature and frequency, the behavior is not linear, and the insulation's response is nonlinear due to the complex molecular behavior and the multiple polarization mechanisms involved. So, an important point in tone delta testing is paying close attention to the measurement of the capacitance. First, capacitance measurement can indicate the presence of moisture inside the insulation. Even a small amount of water molecules, which are strongly dipolar, affect the polarization and their for the capacitance because of the dielectric constants of the insulation change due to the moisture, and its conductive loss is going to be high. Secondly, in equipment like bushings, CVTs, we have some series capacitor layers, and if due to the overvoltage in the power grid, the total capacitance change. So under such stresses, the capacitance will definitely change because some elements are damaged, and the ton delta value may also shift significantly. And in such case, we will get higher capacitance in comparison to the old measurement, because some of our series capacitances are punctured or short-circuited, so we will have higher capacitor value in comparison to the previous measurements, and we can find that okay, our insulation is damaged. Another very important issue is the change in insulation spacing and or oil level reduction inside of the transformer. For example, consider a transformer with a high voltage and low voltage winding, core and tank, which are grounded. So we know that the capacitance between the HV and LV windings, which is which can be calculated by this formula, depends on the distances between HV and LV winding. So if because of the high short circuit current or some mechanical problems, this distance changes, we will have another value for capacitance, and we can compare it with the previous measurements. And if the value of capacitance is changed, we will find that okay, something is happening inside of the transformer winding structure, and these insulation distances are changed. Uh, some of the standards, I think all of IC and IEEE standards, for capacitance value, they say that change between five changes up to 5% is acceptable because of error of the test device temperature. But change between 5 to 10% require investigation to identify the cause of the change, and changes greater than 10% are generally not accepted and may indicate serious issues. We will discuss these topics in more details in upcoming webinars and references for a specific equipment type. The other parameter is tan delta, which indicates the insulation loss. Over time, insulation materials undergo aging and degradations, which can affect their properties. For example, the presence of moisture or cellulose, paper inside the insulation can change its behavior. When the paper inside the insulation overheats, it carbonizes, producing carbon particles that dissolves in the oil. And this leads to increased leachate current and maybe sometimes partial discharge in the insulation. So these localized breakdowns and heats inside the materials increases losses and further degradation of the insulation. Uh, for equipment like for equipment like motors and generators, tan delta measurements are performed at different voltage level in a test known as tip-up test. By measuring at different voltage level, we can find if there is a PD inside of the device or not. So it can help us to find out the insulation problems. One of the main challenges in tan delta testing is its strong dependency on temperature. To have a consistent comparison, measurements are typically you referenced at a standard temperature of 20 degrees. So in all the standards, such as previous version of IEEE C57.12, the 0.90, there were correction factors provided to adjust on delta values measured at higher temperature, for example, 50 or 60 degree back to 20 degree for comparison. For example, if you test a transformer at 30 degree, you would apply temperature correction factor to convert the result to 20 degree reference, and in periodic tests we can compare the delta value at 20 degree. But in new edition of the IEEE correction factors were removed, and it is stated that the experiences has shown that the variation in power factor with temperature is substantial and erratic, so that no single correction factors will fit to the all cases. Now the manufacturer must provide a specific temperature correction factor for their equipment, because a single correction factor cannot be universally applied to all devices. This is because tan delta depends on conduction and polarization losses, which vary significantly uh, depending on the insulation materials and construction. For instance, ABB is guidelines for bushing tests recommends performing routine tan delta test at 90 degree and again at 20 degree. They've said that if the insulation is healthy, the difference between these two values should be minimal. So why? Please take a look at these graphs. Tan delta in OIP bushings is highly temperature dependent, and ABB uh, has published graph showing the tan delta versus temperature for different moisture levels inside the insulation. An important observation from this graph is that at very low moisture levels, for example, 0.1%, the correction factor for converting tan delta from 60 to 20 degrees is close to 1.1. So it's a really small adjustment or correction factor. But if moisture content rises to around 4%, the correction factor can increase dramatically up to 6. So let me show here. We want to correct tan delta values from 60 to 20 degrees. This curve shows it for 0.1% moisture level, and this curve shows it for 4% level of moisture. You can see if the moisture level is increased by increasing the temperature, the dependency of tan delta to temperature is very high. So this means that higher moisture content causes strong increase in tan delta with temperature. To detect the moisture presence inside insulation, one practical approach is measure tan delta immediately after energizing the equipment where the insulation is still warm. Then wait for about 1 to 2 or 3 hours. It depends on the it depends on the device under test. Maybe for bushing it takes 1 hour. So then wait for about 1 or 3 hours until the equipment reaches ambient temperature, for example, 30 degrees, and measure tan delta again. If there is a significant difference between these two measurements, it indicates that the insulation is deteriorating and no longer it's in original condition. In such cases, the equipment should be monitored closely and potentially taken for maintenance or replacement. And the last important recommendation is to measure tan delta at various time intervals within a controlled temperature range, for example, 30 to 35 degrees to facilitate comparative analysis because as we've seen from these slides, the new version of IEEE doesn't support the correcting factors, and we need to have a correcting factor for each equipment from the manufacturer. But maybe for our old substations and old equipment, we don't have such correction factor. So the best way is to measure tan delta at different time intervals at a controlled temperature range. In tan delta testing, there is a concept called frequency sweep or variable frequency power factor or tan delta test, which refers to measuring tan delta at different frequencies. As mentioned earlier, to assess the moisture content inside the bushing insulation, for example, bushing insulation, we measure tan delta at both high and low temperatures. There's an important relationship called Arrhenius equation that helps us to adjust the test frequency based on the temperature. How? How? Let me show. This equation shows that for higher temperatures, we can reduce the test frequency to achieve an equivalent result. For example, instead of testing at 80 degrees at 50 hertz, we can test at 30 degrees but lower test frequency, maybe 9 hertz, 10 hertz. This approach allows us to perform the test under safer or more convenient temperature conditions while still obtaining reliable results equivalent to high temperature testing. We have implemented this capability in Captain 12 Pro version, and this device is this device supports wide frequency range from 1 to 500 Hz. And if we measure tan delta at low frequency, and we found that tan delta is increasing. So we can say that okay, the insulation of the test object has some problems, and maybe we decide to repair it or remove it and install the new device. For insulation modeling, we can use either series or parallel equivalent circuit. If we consider a capacitor and resistor in parallel, the calculated tan delta is the ratio of the active power to reactive power, which equals to 1 divided by omega RC. If we use a series equivalent circuit, tan delta becomes omega RC. So this raises the question about the frequency dependence of tan delta. In the parallel model, uh, the tan delta is inversely proportional to the frequency, means that if I increase the test frequency, the tan delta decreases. But in series model, the tan delta is directly proportional to the frequency. So if we increase the frequency, the behavior of tan delta depends on which model we use. Um, these formulas and these series and parallel models, we cannot use them for wide frequency range. These are just for a single frequency test that we want to model a tan delta at a single frequency. For wide frequency range, for example, from IEEE, we have a curve here which shows that for a higher and wide frequency range, the tan delta behavior is nonlinear, and we cannot model it insulation of the test object just by a series or parallel equivalent circuit. The more complete model for paper oil insulation is the Maxwell-Wagner, where the resistance and capacitance of the oil and the paper are placed side by side. So an important point is that as we decrease the test frequency, the voltage drop uh, across the paper insulation increases, and this larger voltage drop causes the uh, losses in the paper insulation become more. I mean, this range of the frequency. So the lower frequency causes higher voltage drop on paper insulation. If the paper insulation contains moisture, which has known more than 99% of the moisture is held in paper, lowering the test frequency causes a higher loss across the paper insulation, and this means that the sensitivity of the test increases, and we can better assess the moisture content inside the paper insulation. So because of this, a frequency domain spectroscopy (FDS) or dielectric frequency response (DFR) tests are used in on-site tests for um, assessing the insulation and to find out that is there any moisture inside of the insulation or not. But in most cases, if we test tan delta at a frequency range of 1 to 500 hertz, and the device under test is in a bad condition, I mean at low frequency, the tan delta is increasing. So I would say that okay, the device under test has problem, and we should do some maintenance for repair or remove it and install a new device. So there are some modes for measurement of tan delta which test kits support them, and we want to discuss about these measurement modes. First mode is called UST, ungrounded specimen test. In the UST mode, we test capacitors that are not connected to ground. In other words, both terminals of the capacitor are available to us, and we can connect the test device directly to terminals of the device. The other two modes are called GSD and GSDG, which are used for testing capacitors which one side is grounded and we cannot disconnect them from ground. In GST mode, or capacitors which are connected to the test device is measured, but in GSTG mode we can guard or bypass some capacitors by connecting them to the input terminals of the test device. Let's see what's happening inside of the test device when we select modes. So we have three capacitors which are connected to Kaplan 12. For example, Kaplan 12, a high voltage terminal uh, is connected to all of them. C1 is connected to input A, C2 is connected to input B, and C3 is ground. All currents come to the device, and we have a switch box or a matrix relay inside of the device, which when we select test mode in the software, these relays works based on these modes, and we can measure or bypass some currents. So when we select USD-A mode, current passing through the input A go to the ammeter, and input B and ground current are bypassed or guarded. So the back of the ammeter is called guard, and when we don't want to measure a current of the test object, we can connect it to the guard. So if a test object is connected to the guard, the current passing through it uh, is not measured. And in this case, when we select USD-A mode, current passing through C1 is measured, but current of C2 and C3 are guarded, so we will measure just C1 at USD-A mode. In USD-B mode, just C2 is measured because current passing through C2 is connected to the ammeter, but C1 and C3 currents are bypassed and guarded. For USD-A plus B, we can measure C1 plus C2. In DSTG-A mode, current passing through the input A is connected to the guard point, and input B and ground currents are measured. So C2 plus C3 is measured in GSTGA mode. If we select GSTGB, current passing through C1 and C3 are measured, and C2 is guarded. In GSTGA plus B, just C3 is measured. And finally, in GST mode, the device measures all capacitors which are connected to the inputs or ground. So let's summarize the measurement modes. In USD modes, each input which we select is measured. For example, in USD A mode, input A is measured. In GSTG mode, when we select an GSTGA, input A is guarded. In GSTGB, input B is guarded. And in GSTGA plus B, A and B are guarded. And finally, in GST mode, or inputs, all input currents are measured. Okay. One of the common issues in field testing is the appearance of a negative tan delta value. But does such a value have any physical meaning? The short answer is no. A negative tan delta implies a negative resistive current, which is physically impossible because we don't have a negative resistance in real world. And sometimes it could mean there is a large inductive component in the current. However, in tan delta testing, we are not evaluating the inductive behavior of the equipment. So the test setup is designed to eliminate the inductance by short-circuiting the terminals, for example, in a transformer, so that only the capacitive behavior of the insulation is measured. There are some reasons that causes we measure negative tan delta in on-site test. First one is um, high surface leakage current on bushings and insulators. Contaminants combined with moisture form a conductive film on the surface of the bushings or other HV equipment. This can be modeled with an equivalent circuit where resistor R is placed parallel with the insulation capacitance. When a high voltage is applied to central conductor of the bushing, the leakage current uh, doesn't only pass through the internal capacitive layers, but also partially flows over the surface, adding an unwanted component to the total current measure. So the surface leakage current can distort the measurement and may even result in negative tan delta, which, as discussed, is physically meaningless. For solutions of these problems, firstly, clean the surface of the insulation and thoroughly before testing. Secondly, avoid testing that during rainy or highly humid weather conditions. Wait for sunny and dry conditions, and use the guarding technique. Uh, for example, you can attach a metallic strap below the HV terminal of the bushing. I mean something like this, and connect it to the guard terminal of the test device. So this strap collects the surface leakage current and route it away from the measurement path and ensuring only the true dielectric current is measured. So this technique helps us to eliminate the influence of surface currents and leads to more accurate tan delta result. Other one is the not short-circuited windings. The presence of inductance in the circuit can lead to negative or abnormally high tan delta values. If the inductive current flows through the system, it can distort the measurement. For example, in this case, the 400 kV bushing is tested, and in the first test, the transformer was not short-circuited, and voltage was applied only to the bushing's high voltage terminal. The measurement showed a tan delta of 0.61%, which is really high value for a new bushing. But after short-circuiting the transformer windings, the measured tan delta dropped to 0.24%, which is about 2.5 times lower than the previous measurement. This demonstrates that if the bushing is tested without properly short-circuiting the transformer, the resulting tan delta may be significantly high or even negative. Another reason is the presence of an electrostatic shield. Normally, we consider three main capacitors in a transformer insulation system: CL between the capacitor between the low voltage winding and the grounded core. I mean this capacitor, CHL, capacitor between high voltage and low voltage windings, and CH, capacitor between HV winding and the grounded transformer type. In some two-winding transformers, especially for power generation transformers or renewable energy renewable energy uh, transformers, there is an electrostatic shield is placed between HV and LV windings and directly grounded. This shield prevents high-frequency overvoltage caused by switching or lightning surge on the HV side from transferring it to the LV side, which some manufacturers use this technique. So, because this shield is grounded, the CHL capacitor effectively disappear. When measuring with a tan delta device under these conditions, the measured value mainly reflects only the stray capacitance of the bushings and other components, which are typically in order of a few hundred picofarads. This can result in very high or even negative tan delta values. In this case, the measurement and evaluation of the CHL capacitor is not necessary. Another case arises in three winding transformer. For example, when testing the Three winding transformers, in this case CLT, the capacitor between LV and tertiary winding. The HV winding is connected to the guard terminal of the tan delta test device. So, if we want to measure CLT, there would be just a stray capacitance between HV and tertiary winding, and in this case also we will get a wrong value, maybe negative or high positive tan delta value, and also it's not necessary to evaluate the condition of LT capacitor in this case. Another reason is the electromagnetic interference, EMI problems. So another important factor is the presence of noises in the system. Consider a transformer installed in a high voltage substation where overhead power lines with conductors run near the transformer. These conductors induce the voltage, so we call the stray capacitor capacitance between the overhead line and transformer bushing C1. The induced voltage uh, causes current to flow through the maybe CH1 capacitance of the transformer to the ground. And if we want to measure CH, because of this capacitive divide, I mean C1 and CH, we will have some voltage and HV terminals of transformer and also some current passing through the CH to ground. To avoid this, it's recommended to fully isolate the transformer, short circuit all terminals, and test that frequency near to 50 or 60 hertz and not exactly at power grid nominal frequency. Sometimes, if proper insulation is not done and the transformer terminals are only connected transformer terminals are connected to circuit breaker, and we say, okay, the circuit breaker is open and we've energized the transformers. But the question is that in these cases, we will get a wrong value of for tan delta, especially for CH or CL of the transformer, which are measured in GSD mode, because we will have some surface leakage currents through other components in the substation. And if we measure CH and CL, the tan delta and also capacitance of these equipment come to measurement, and we are measuring all of the capacitances in parallel with CH and all of the losses. So to obtain accurate tan delta results, the transformer must be properly isolated, and I mean we should isolate the transformer from the bushings and short circuit them together to eliminate the noise and leakage current during testing. And the final point is insufficient test voltage at substation. Applying low test voltage such as 1 or 12 kV can lead to inaccurate and delta results, because maybe there are some induced voltage in the system, and we apply lower test voltage, our test fit accuracy will be very low, and we cannot measure tan delta with high accuracy, or our test results will not be repeatable. In such cases, we will have some maybe negative value of tan delta. So to ensure accurate and repeatable measurements, it's essential to perform tan delta testing at higher voltage, for example, 10 or 12 kV, because this helps to guarantee sufficient sensitivity and confidence in evaluating the insulation condition and predicting future performance. Uh, and finally, negative tan delta value should never be accepted as a final result without investigation. Instead, we should troubleshoot the test setup, connections, and equipment before reporting the result. Blindly accepting and defaulting stats values can lead to incorrect conclusion. This is Kaplan 12.
This is the part that I think, we have a few more slides here to tell you some of the products that WiseGrid Energy basically have, specific to tan delta, Captain 12, which is a 12 kV tan delta and capacitance test set. Basically, it has a pretty good power range, 12 kV, 300 milliamp. It can cover pretty much any good, like the largest units of power transformers or breakers, etc. And like, as I think I touched about it, you can have a frequency range of 1 to 500 hertz. There are some options, in the market, but they do something like 10 hertz or 20 hertz to 500 hertz, which is fine. But I really like the 1 hertz here, because I get the lower that I go, I get more information about moisture ingress and some contaminations, etc. I mean, this is not an ideal number, I tell you technically, but the lower the better here. Accuracy, but I mean, this is the best in the market so far. That's what I was trying to say. And there are some also accuracy. I mean, for some people that they're very picky, I think still this is probably the best accuracy in the market too. The nice thing about these units that the colleagues that they put together, it's pretty modular. So if I have hypothetically, if I'm in North Pole, for example, and my my system is down, if somebody's and through a remote diagnostics, you can find out which module is broken, and if somebody send me that specific module, probably I can replace it on site too, in worst cases, which is nice. So, like having a modular design, I think that's a big advantage here. So, I think we already talked about this unit, and this is a specific to tan delta measurements, not only power transformers, for other assets too. I think that's what we talked about it. Hossein explained the definition of tan delta, the importance of CNDF, how it's related to the temperature and frequency. I mean, we couldn't go too deep. Obviously, you can talk about it a lot, and understanding negative tan delta, I think that was a quite highlight, and he mentioned four scenarios here, 4 or 5. And I think that's it from our end. And we really appreciate all you that you bear the technical difficulties, and also my bad voice too.